Hello, my name is Mark. I'll be speaking about an optimally competitive algorithm for maximum online perfect bipartite matching with i.i.d. arrivals. Alright, that is quite a mouthful, so let's get started by breaking it down. First of all, what is the online bipartite matching problem? In the online bipartite matching problem, we have a set of workers, and at each time step, a job is going to arrive. When that job arrives, we will see a set of utilities for assigning that job to each of the workers. We need to make a decision before the next job arrives. We're going to assign that job to one of the workers. That job is assigned irrevocably, and the worker is busy after assignment for the remainder of the problem. After we've done this assignment n times for n workers, all of the workers are busy, and the result is a perfect matching between jobs and workers. Our goal is to develop an algorithm for assigning jobs to workers that maximizes the sum of the utilities of all of the assignments. Thus, we have the maximum online perfect bipartite matching problem. Now, I've told you that these jobs arrive, but I haven't told you how they arrive. There are three common arrival models that are in the literature. The first is the strongest adversary. That adversary is allowed to choose both the jobs, and in this case, when I say choosing the jobs, I mean the set of adjacencies to the workers, the set of weights, the set of utilities for matching workers to jobs. So the adversary is allowed to choose those jobs and also the order in which they arrive. You can weaken this slightly to the random arrival order model. In this model, the adversary, again, is allowed to choose the jobs, but no longer chooses the order in which those jobs arrive. And finally, there's the i.i.d. model, where the adversary doesn't necessarily select jobs, but selects job types. And then jobs are drawn i.i.d. independently and identically distributed from that distribution. There are a lot of potential application areas of online bipartite matching. Many of these are discussed in the relevant literature. I'll just talk about a few of them. For example, you could imagine that the workers are doctors, and the jobs which are arriving to the system are patients. You could imagine that the workers are operators in a call center, and the jobs or the callers which are arriving are calling in. You could imagine that the workers are drivers in a ride-sharing system, and the jobs that are arriving are people that are requesting rides in that system. In all of these cases, there are two things that I would point out. The first is that the i.i.d. model is actually a fairly realistic one. After all, there aren't adversaries sitting outside of an emergency room deciding which patient is going to show up. There are random processes that affect these arrivals, and so an i.i.d. model is reasonable. Furthermore, it makes sense in a lot of these cases to group the jobs into job types. For example, patients only arrive with a certain set of possible maladies. Callers only arrive with a certain set of problems, and callers with the same problem can be treated pretty similarly. And riders only will request rides from certain locations, not like it's completely arbitrary. And within a region, you could sort of group riders together. So in all of these application areas, the i.i.d. model with job types is fairly reasonable. In fact, to use the more general terminology of queuing theory, whenever jobs arrive to a system according to a homogeneous Poisson splitting process, it makes sense to model the matching within that system as an i.i.d. Arrival by job type. So in order to actually solve this problem and to describe our algorithm, we're going to introduce what we call the expectation graph. In this expectation graph, we again have workers on the left-hand side. But on the right-hand side, instead of having the actual jobs that arrive, we have the job types. Now, the distribution over the job types is represented by these weights at the job types. And those weights represent the expected number of arrivals of that job type. So in this case, you can see that on the left-hand side, there's a weight of 1 for each worker. And on the right-hand side, there are weights which add up to 5, as you would expect, because there are going to be 5 arrivals. You expect the expectation should sum up to 5. Furthermore, there are utilities along the edges. Those edges represent the utility of assigning a worker to a job of that type when that job type arrives. To assess the performance of our algorithm, we're going to use the concept of competitive ratio. The idea in competitive ratio is to compare the performance of our online algorithm, which is making decisions on the fly, to an algorithm which knows the entire sequence of arrivals in advance. So that's an offline algorithm that computes the maximum matching in the graph retrospectively. It's how well we could have done, it's how well we did relative to how well we could have done. And in this minimization here, the expectation on the bottom over opt of G is the expectation over the possible random arrivals, the random i.i.d. arrivals. And in the numerator is the expectation over both the arrivals and whatever internal randomness we have in our algorithm. As you can imagine, with so many potential applications, there's been a lot of work on online matching problems. It started off in the 90s with the famous 1 minus 1 over e approximation. That was for the maximum online imperfect matching problem. And in the imperfect matching problem, you're just allowed to ignore jobs, whereas in the perfect matching problem, you are required to assign every job. You can see a trend in the maximum imperfect matching setting. In that setting, as we weaken the adversary, the competitive ratio gets better and better. It gets closer and closer to 1. On the other hand, people have studied the minimization version of this problem. In the minimization version, it only makes sense to consider perfect matching, because if you consider imperfect, then you can just ignore all the jobs, and you get a utility of 0, which is the minimum utility. So it makes sense, given that there's work on the maximization, work on the minimization, to consider what happens if you change the maximization setting to a perfect matching. And unfortunately, in the case of an adversarial arrival model, it's not possible to get a non-trivial approximation rate, non-trivial competitive ratio. So what we're interested in is weakening the adversary to the i.i.d. adversary. And in that case, in this work, what we show is that we can attain a 1/2 competitive ratio. And furthermore, the 1/2 competitive ratio is actually the best competitive ratio possible. So I'm going to show the impossibility result first. I'm going to show that it's impossible in this setting to get a competitive ratio better than 1/2. So consider this expectation graph. We have n workers and n plus 1 job types. There's one job type, J0, which occurs with very high probability, with probability 1 minus epsilon. And so the expected number of arrivals is n times 1 minus epsilon. So this job occurs with a very high probability, but its utility when matched with each of the workers is 0. On the other hand, there are n jobs which arrive with very small probability, and they have only one worker to which they can be assigned. And when they're assigned to that worker, they get a utility of 1. If they're assigned to any other worker, they get a utility of 0. And this may seem a bit contrived, but I would actually argue that there are situations in the online matching problem, there are application areas where you have a lot of jobs that arrive that are pretty low value, but then every once in a while a very high value job arrives, which needs to be matched to a very particular worker in order to get that high value. So it's not entirely contrived. So we're going to analyze this by considering what happens when only one useful job arrives. We're going to condition on that event. So conditional on that event arriving, what happens? Well, the offline algorithm is going to get a utility of 1. The reason it's going to get a utility of 1 is because it knows which of the jobs is going to arrive, so it makes sure to leave that worker free until the job arrives and then just assigns that job to that worker. Now, in the online algorithm, we don't know which of the useful jobs is going to arrive. And so if that job is the first one to arrive, then we get a utility of 1 because the worker will definitely be free. If that useful job happens to be the second one to arrive, well, one of the workers has to be busy. And if the job that arrives the useful job that arrives corresponds to that worker, then we don't get the utility. That happens with probability 1 over n. So with probability n minus 1 over n, we do get that 1 unit of utility. We can continue this logic. If the useful job is the second one to arrive, then we get its utility with probability n minus 2 over n. Because there are n minus 2 workers that are available, so the probability that it has a job type which corresponds to one of those workers is n minus 2 over n, etc. We continue this logic all the way down to the nth arrival. At that point, only one worker is free. So the probability that the nth job type is the one that actually corresponds to that worker is just 1 over n. And this, if you calculate this, gives you approximately 1/2. Okay, so how does that actually give us the competitive ratio? Well, we conditioned on the event that just one useful job arrives. If 0 useful jobs arrive, both the online and the offline algorithm score a utility of 0. And because the useful jobs arrive with a very small probability epsilon, I'm going to claim that the probability of 2 useful events, or 2 useful jobs arriving is effectively 0. So we just need to calculate the probability, the utility gained from 0 useful jobs arriving times the probability of 0 useful jobs arriving, plus the utility of 1 useful job arriving times the probability of 1 useful job arriving. And in that case, the probability of 1 useful job arriving cancels out, and we get a competitive ratio of 1/2. This is a bit hand-wavy, but if you take a look at the paper, you can see a full rigorous argument for this, that you cannot get a competitive ratio better than 1/2. Rather than describe the algorithm directly, I'm going to give an example of our algorithm in action. Our algorithm starts off by solving an offline problem on the expectation graph. That offline problem is a transportation problem, which is essentially a maximum matching but with weights. In this case, the solution to our transportation problem is as follows. Now we're going to use that transportation problem to guide our online decision making. Here's the realization graph. Let's say that first a job of type 3 arrives. We're going to look at J3 in the transportation problem and notice that it is adjacent to workers 4 and worker 5 with weights 1/2. So we're going to randomly select with probability 1/2 worker 4 or randomly select with probability 1/2 worker 5 and call that our preferred worker. If the preferred worker is available, we're done. We just assign the job that arrived to that worker. We can continue this process. A job of type 1 arrives. Notice that jobs of type 1 are adjacent to worker 1 with weight 1, worker 2 with weight 1, worker 4 with weight 0.5. So we choose worker 1 with probability 2/5, worker 2 with probability 2/5, and worker 4 with probability 1/5, proportional to the weights. Worker 2 is our preferred worker. The preferred worker is available, so we're done. A job of type 2 arrives. Worker 3 is chosen as the preferred worker. Good. Another job of type 2 arrives. Worker 5 is chosen as the preferred worker. Good. Now, when a job of type 3 arrives, in this case, it wants its preferred worker, which is preferred worker 4. However, preferred worker 4 is not available. So, instead, the job is going to randomly select from all the remaining available workers. In this case, it's just worker 1, and it chooses worker 1 as the worker to which it is assigned. Now, this random step might seem suboptimal, but in fact, we're going to see that in the worst case, it's as well as we can do. So for the sake of worst case analysis, the randomness is just fine. This is the final realization graph that we get and the corresponding utilities for a total utility of 6. So just to summarize what happened, the first thing we did is solve an offline transportation problem in the expectation graph to get a flow. Then, whenever a job arrived, we randomly drew a preferred worker, and that random drawing occurred proportional to the flow. If the preferred worker was available, we assigned them. That was it. Otherwise, we randomly assigned one of the available workers to the job that had just arrived. I'm not going to give the full proof of correctness of the 1/2 competitive ratio. However, I am going to describe the intuition behind 2 key lemmas that I think are really insightful. The first key lemma is this. It essentially states that at every time step, the preferred worker is chosen uniformly at random from the set of all workers. Now that might seem a little bit confusing, because when I just described the algorithm, I said that conditional on the job arriving of a certain type, we take a weighted sample of the workers to decide which worker is the preferred worker. However, if we don't condition on the type of the job that just arrived, the sampling looks uniform. To put that differently, you can imagine that if you were just looking at the set of workers that were being chosen as preferred workers at each time step, and you didn't know which jobs were arriving, it would look to you as though the algorithm is sampling from the workers uniformly. Here's an example which I think will give the entire intuition for how the lemma is proved. Let's say we wanted to calculate the probability that worker 1 is selected as the preferred worker. For that to happen, first, the job of type 1 has to arrive. That occurs with probability 2.5/5, or 1/2. And then the worker of type 1 has to be chosen as the preferred worker, conditional on job type 1 arriving. That occurs with probability 1/2.5, or 2/5. If we put that together, we get the probability of worker 1 being chosen is 1/5. Now let's look at the probability worker 4 is chosen. There are 2 ways it could happen. Either job type 1 arrives, and then worker 4 is chosen with probability 0.5/2.5, or a job of type 3 arrives, and worker 4 is chosen with probability 1/2, 0.5/1. If we add that up, we get, again, 1/5. And you can start to see that the reason for this is because the actual arrival of the jobs cancels out. And so because each worker has a total weight adjacent to it equal to 1, each worker at every step is equally likely to be chosen as the preferred worker. Now remember what happens when a job arrives and its preferred worker is busy. If its preferred worker is busy, then it gets assigned to a random worker from the set of workers that are available. Which means that this probability distribution of 1/5, 1/5, 1/5, 1/5 gets redistributed to a probability distribution of 1/2. Because there was a 1/5 chance originally of choosing worker 1, a 1/5 chance originally of choosing worker 5, and a 3/5 chance of choosing workers 2 through 4. But then, if workers 2 through 4 were chosen as the preferred worker, worker 1 or worker 5 were randomly selected. So in total, this job that's arriving is choosing from the available workers uniformly at random. That brings us to the statement of the next lemma. Because at each step, unconditional on which job type is arriving, we are selecting from the available workers uniformly at random. That means that the probability any particular worker is available at time t can be expressed in this formula. So now this is going to look kind of familiar. The probability that the worker we want as our preferred worker is available at time 1 is 1. The probability that the worker we want as our preferred worker is available at the next time step is n minus 1 over n. The next time step, it's n minus 2 over n. That goes all the way down until time step n, where all but one of the workers are already busy. So the probability that the preferred worker we want is available is only 1 over n. And so in expectation, on average, we get our preferred worker 1/2 of the time. Now, showing that we get the preferred worker half the time is not quite the entire proof. But here's a summary of the key ideas that are needed to round out the proof. First, we have the idea that we already used, that the transportation problem on the expectation graph has been guiding our online algorithm. We're not the first people to do this. There have been other people that have taken similar approaches, but we're the first people to apply it to this problem. But at any rate, we would use that transportation problem, as we just did, to bound the performance of our online algorithm. And that's where that 1/2 would come in. We would say that, okay, because we know that at least half the time we're getting our preferred worker, and the transportation problem represents always getting your preferred worker in expectation, well, if we're getting our preferred worker at least half the time, our performance will be at least half the transportation problem. On the other hand, we could show that the optimal offline algorithm is bounded above by the transportation problem. And the reason for that is essentially because the expectation over all the optimal solution forms a feasible transportation solution, which means that the optimal transportation solution has to be better than it. And together we could combine all this to show that our competitive ratio is at least 1/2. So to conclude, in our paper, we showed that we described an algorithm which has a competitive ratio of 1/2, and that 1/2 is the best possible competitive ratio for this setting of the online bipartite matching problem. So our algorithm is tight with respect to competitive ratio.